Okay, guys, my name is Alisher. I'm a machine learning engineer. Now we are going to look into optimization algorithms. Uh, okay, let's recap what Mustafa and Dimitris explained. In neural network training, we have several steps. The first one is to initialize the weights so that we can start from particular point and start to optimize our network. And this weights can be initialized by uniform distribution or Gaussian distribution, or there's another initialization method, is cherry method, which is kind of smarter initialization method. It's calculates the previous layer number of neurons in previous layer and kind of initialize the weight of the next layer regarding the number of neurons in the previous layer. And after initializing the weights, we usually do forward pass. And that means start to feed input and like kind of for classical neural network, just multiply with weights and apply some activations and so on, and go to until the output layer. So this is the forward pass. The forward pass can be things like transformation of input into different hyperdimensional space. After getting the prediction, I mean in training stage, after getting the outputs of neural network, we calculate the error loss or loss, and then we want to minimize this loss after training, after some iterations. So we want to update the weights so that the loss could be converged to local minima or global minima. That means minimize the loss. So we need some kind of rules for updating the weights, right? So and there can be many rules, like you can just multiply loss with the weight, or you can add, or any kind of function you can use in updating the weights. So we want to update the weights with particular policies so that the predicted output should be closer to our target output. That means we want to minimize the error function. In order to do this, we need to calculate the loss or error, and we need to decide on what kind of rule or what kind of policy we are going to use in updating the weights. And after updating the weights, we do iterations like from backward and forward, backward, forward, backward kind of cycle here. And hopefully you are going to converge to local minima or global minima, hopefully. So in order to kind of understand how to update the weights, let's try to demonstrate OR gate. OR gate means just doing OR operation between 0 and 1. This is our training data. This is our training data. We have 4 samples in our training set. 4 data samples, and 1 epoch here means 4 iteration. In each iteration we use if we use only 1 sample in 1 iteration, 1 epoch means 4 iterations for this data set. And we are going to use loss of L2 loss. To calculate the loss function, we are going to use L2. And optimization, let's use SGD, stochastic gradient descent. We are going to go into details in the next slide as well. Basically, as you can see, the OR gate is not linear function because there's no linear fitting. You cannot fit any linear function to achieve the OR gate's functionality. So it's impossible to solve OR gate problem with single layer network with 2 neurons and without any activation. That means if you use single layer, there is no nonlinearity in your network if you don't use activation functions, of course. Yeah, OR gate is nonlinear function. To solve this problem, to solve this OR gate problem, you have to use either multi-layered neural network or some kind of activation functions to put some nonlinearity into your model. But let's try to just try single-layer neural network. That means it's impossible to solve this problem, but we are going to see how weights are updated. So yeah, let's start with the first iteration. And this is the x and y is 0, and we want to get z 0, right? Oh, I did wrong here. I'm sorry. This should be 0. Let's go on with the second iteration because I did the wrong calculation there. So let's start with the second iteration. The x is 0, y is 1, and let's assume we initialize the weight as 0.1 and minus 0.2. So what we want as output is 1. This is the target output here, 1. And we got the prediction of minus 0.2, right? So there are some difference between target output and predicted output. So we have to calculate the loss. So how good or how bad our model performed on this iteration. So in calculating loss function, we use L2 distance. That means target output minus predicted output and square it and divide it by 2. So it is 0.72. So we have 0.72 loss function equals 0.72 in this iteration. And so we got the loss, and we want to update the weights with respect to this loss value. So let's calculate the gradients. So in order to update the weights, we need to calculate gradients. Gradient means to find the slope and the direction of the loss function. Here we use stochastic gradient descent. So the formula is here: target value minus predicted value multiplied by the weight. So in order to update this weight, we are going to multiply the previous value of this weight and target minus predicted. So target minus predicted is this, multiplied by 0 and added to this the previous one, previous value. So yeah, we updated the weights. So there's no update for here because no change in gradient of this weight, but we updated this one as 1. It was 0.2 minus 0.2, and we update the weight as 1. So after updating these weights, let's calculate the predicted output. 0 times 0, 1, 0, 1 times 1, 1. So the target output was 1, and after updating the weights, predicted output is also 1. That means loss before update was 0.72, loss after update was 0 for this iteration, of course. And let's go on with the next iteration. Is the just reverse of the previous one, 1, 0. So we have we need 1 as an output, as a target output, and we predict 0.1. And again, we calculate the loss is 0.4. And after updating the weights, it becomes 1 and 1. So loss before update was 0.4, and after update, it was 0. So as you can see, our network is directly overfits to that sample during the training. As a last iteration, our weight was 1 and 1, here 1 and 1, so we start with 1 and 1. Target output should be 1, but we predict 2. The loss is 0.5, and we are going to update the weights as 0 and 0. Here, loss before update was 0.4, after update it was 0.5. So as I mentioned before, it's if you repeat these iterations, I mean, if you go, for example, 10 or 100 epochs, you cannot achieve OR gate function because OR gate is nonlinear function, and we are trying to solve this problem using only linear mappings. So it's not possible to solve this problem, but we saw how to update the weights.
You mean it doesn't compile, you mean the loss function doesn't go to 0. That's what you mean, right? I mean, there's no non-linearity.
Yes.
Loss update doesn't really
converge. If you use, for example, 2 layers kind of thing, so in 2 layers there's some nonlinearity. After some epochs, we may converge to global minima, but using this model.
I understand, but in your example, those before update and after update doesn't go to 0. That's what.
Yeah.
Yeah, right. I mean, after 4 iterations, the loss function doesn't decrease.
Yes, because this loss.
That is a manifestation of what you're saying.
Yeah, exactly. Yes, it's kind of not stable, fluctuating. To train the model to converge to global minima, the loss function is very crucial. It depends on the task. For example, one loss function is better for particular task, then another one is better to other task. So there's no global, the best loss function. You have to choose the loss function according to your task, or you have to just try some of them. Also, weight initialization is also important. For example, so let's see this one, this shape. Let's assume this as a loss function. For example, let's assume we start the weights here, something like here, somewhere here. The convergence would be faster, right? If you start here, the convergence would be a bit slower. Even if the weight initialization is important for fast convergence, in deep neural network, since they are so deep neural networks, loss function is not something like that. This is kind of very complicated hyperdimensional space. So it really doesn't matter how did you initialize your weights in deep neural networks. And also activations is important. So for example, in our previous example, if we add some kind of activations, that means if we add some kind of nonlinearity to our model, the loss can be a bit lower than this one. And also data processing is also important. Before feeding the inputs into neural network, we have to normalize. There are several kind of normalization. One is zero mean and one variance normalization. So it's important to normalize your inputs before starting the training. So another thing is learning rate. Learning rate is like we calculate the loss, and using this loss we update the weights. Learning rate is value between 0 and 1. That means if that is 1, you directly use that gradient of that weight to update the weight. if this is 0, there wouldn't be any learning because it's multiplied by 0. And so that's why if learning rate is smaller, that means we got the gradient and multiplied that gradient with small number like 0.0001. That means we are going to update the weights very slightly. If the learning rate is larger, like 1 or 0.9, and the convergence would be faster. And the other key point in training the neural network is optimization algorithms. How do you update your weights having the loss of that iteration? And let's introduce two concepts here that are global and local minima. So forget about deep neural networks. Just consider function, any function. Like, for example, here we have a function f of x. Input is x, and output is cosine 3 pi x over x. So this is the function. This is nonlinear function and univariate. That means there's only one parameter of this function. And this is the plot of this function. So as you can see, there's kind of hills and local minimas or global minimas. So global minimum is the lowest point in our graph. Like this is the local global minimum. It's the lowest one. And this is the global maximum. This is local maximum, and this is local minimum. In deep neural networks, there may be one global minimum, but there may be 1,000 or 10,000 of local minimas. So there are a lot of local minimas, but single global minima. Single global minima means exact solution of your problem. So yeah. So this was the just random function, and in the right you see in the right there's a function that is the loss function of a deep neural network. This is multivariate. That means there are a lot of parameters of this loss function, and there are some nonlinearities inside the model. So the loss function is also nonlinear, and it lies on hyperdimensional space. So what's the input of this loss function? The input is the weight of our model, weights of our model. And so loss function can be something like that if there's only one parameter. But usually this is very simple graph. So it's very kind of similar to that one. But in reality, the loss function of deep neural network is something like this. Yeah, so this is the hyperdimensional space. There, for example, let's assume 1,000 dimensional space, and there this kind of I'd say very complicated, very complex space. So here, this point is global maxima. This is local minima, and this is global minima. And there can be a lot of local minimas as well. Yeah, usually the loss functions of deep neural network is not lies not in two-dimensional space. There may be 100 or 1,000 or maybe more dimensional space. Yeah, so regarding random weight initialization, let's assume we initialize the weights something here. That means we initialize the weights which results the loss function which is here. So this is just random. We could start here or here. That's not a problem. So our goal is to find the global minima. In theory, we want to find the global minima. That means we want to exactly solve our problem, right? But since deep neural network is not a deterministic approach, so since the deep neural network is like probabilistic approach, you may not reach to global minima always. Maybe you never reach to global minima, but still you can find the local minimas in this hyperdimensional space. But it's still okay to converge to local minima to solve our problem. So here's the quote from Deep Neural Network book. Yeah, there can be only one global minimum and multiple global minima of the function. It is also possible for there to be a local minima that are not globally optimal. In the context of deep learning, we optimize functions that may have many local minima that are not optimal at many saddle points. Saddle points kind of flat spaces in hyperdimensional space. And all of this makes optimization difficult, especially when the input to the function is multidimensional. So we have, for example, let's assume we have 10 by 10 image. So there are 100 parameters here. But yeah, we usually try to classify images with 255 to 255. So this is really multidimensional input. And we therefore usually settle for finding a value of that is very low, but not necessarily minimal in the formal sense. So you don't need to reach to global minima. It's okay. It's still okay to reach the local minima as well. Yeah, there's no one clear optimization algorithm that outperforms the others. It's just kind of users' familiarity of hyperparameter tuning. So let's start with optimization approach. The first one is gradient descent. Basically, gradient descent is not one of the methods. Gradient descent is the kind of super name of all kind of gradient-based optimization algorithms. So what does gradient descent is? So this theta on the left is the previous our new weight, and this is our previous weight. This is learning rate. New is learning rate, and this is the gradient of our weight with respect to loss function. I mean, gradient of loss function with respect to weight. So yeah, this is our loss function, L2 loss function, and we want to find the direction of gradient to how to say to make some steps towards local minima. So yeah, let's compare the batch gradient descent and stochastic gradient descent. Maybe we have to read this first. So batch gradient descent means let's assume you have a data set with, for example, 100 samples in training. In batch gradient descent, you run all over these 100 samples and compute the gradients of compute the loss of all iteration, and then update the weights. So that means weight update is performed in each epoch, not in each iteration. So run through all training samples, then update the weights. So this kind of optimization is a bit slower, and you can use this kind of gradient descent, batch gradient descent approach when you have a really small number of samples in your training data set. So here's the how batch gradient descent works. And the other gradient-based optimization is stochastic gradient descent, which is calculate an error for single sample in single iteration, calculate some losses, and directly update the weights using this loss and get another iteration, another batch, or another sample, and to do the same for this one. And it iterates over all training samples by updating the weights in each iteration and or in each samples. So as you can predict, the loss like convergence wouldn't be stable in this way, but that means high variance. But this is good because for example, let's assume after some iteration we got this point, for example. So you see there's some local minima behind this one. So we got this local minima, and in stochastic gradient descent, since the gradient is too high and non-stable, so you have many chance to cross over this hill and find the better local minima, or like this. In gradient descent, in batch gradient descent, you may not go out from this local minima to this one, which means the stochastic gradient descent is not stable, but it's good for us because it helps us to find maybe better local minimas in the space.
But can the opposite also happen, where maybe you're in that deepest global minimum and then stochastic gradient descent bounces you out and you get worse?
Exactly.
Go away from the global minimum.
Yeah, exactly. So we are going to talk about momentum to prevent this issue. Yeah, as you said, there's another problem to go out from the global best local minima. So there's another concept, which is momentum. So momentum helps to accelerate the SGD in the relevant direction and dampens oscillations. So what is momentum? Momentum is the momentum as a fraction of gamma of the last update state. Like we had in stochastic gradient descent, we updated the weights with the last iterations information, but here momentum uses the previous update information and adds to the current one. What does it mean? Okay, so there's analogy for momentum. So let's assume there's hill, something like that, and you push a ball from the hill, and so basically, so let's assume this kind of space. We have this kind of space. When we push the ball from here, there may be possible to reach here and reach to other minima, right? So the momentum solved this issue to slow down the learning rate when reaching to the local minima. Yeah, basically when we push the ball, it accumulates the momentum, becoming faster and faster on the way. And similarly, momentum term increased for dimensions whose gradients point in the same direction. So here, so SGD was like oscillating. So this is our global minima, right? Okay, this point and this point. So in SGD, it was like oscillating into other dimensions which are not going to global minima. But momentum helps to go faster to global or local minima. So it kind of controls the direction of current weight update using the previous iteration update. So but there is still the problem which I mentioned just now, which is there's still problem possible to go out from the local minima or global minima. So this can be solved by controlling the learning rate during the training. So AdaGrad is another optimization algorithm, which adapts the learning rate during the training, which means takes smaller steps with frequently occurring features and larger updates for rarely occurring features. This is very good for sparse data. If you have sparse data, using AdaGrad is almost better than stochastic gradient descent. Yeah, and the another problem here is like, since we decrease the learning rate in each iteration, there's possibility to become learning rate 0. That means there wouldn't be any training after some iterations, right? So this is the issue in AdaGrad, and another optimization algorithm is RMS probe, which solved this problem in some sense, which is divides the learning rate for a weight by a running average of magnitudes of recent gradients for the weights. This is kind of not directly dividing by fixed number, instead dividing the learning rate using the previous iterations weights gradients. So this is something like memory, like keeping in memory the previous steps and then changing the learning rate. That means, so that means here gradient is large and here is smaller. RMS probe is doing something like this. When you reach to minima, local minima, the learning rate is like slowing down. And the other one and the last optimization algorithm we are going to mention today is ADAM. ADAM is adaptive moment estimation. It's kind of a bit complicated, but in gradient descent we use the first order derivatives of weights of loss with respect to weights, but ADAM uses the second derivative as well. It's kind of behaves like a heavy ball with friction, so that's why it prefers the flat minima in the error surface. In most cases, ADAM works well and outperforms other adaptive techniques. So ADAM, RMS probe, and AdaGrad are adaptive optimization methods, and in most cases, ADAM works better than other adaptive techniques. So the problem arises here is which algorithm to use in our problem, right? So if you have sparse data set, use one of the adaptive learning rate methods, which was controlling the learning rate during the training. If you want to fast convergence in deep neural network training, then use ADAM or any other adaptive learning rate methods. So in a conclusion, it's always better to use adaptive learning rate methods, which are ADAM, RMS probe, and AdaGrad, and there are also some other kind of adaptive learning rate methods as well. And it's better to use these methods if your data set is very sparse. So let's take a look on other concepts like underfitting and overfitting. So overfitting concept is very important in training deep neural networks, especially because it tells us, as Dimitris mentioned, it tells us if our model memorized the training samples or not, or if it well generalizes the test samples or not. So underfitting is poor performance on the training data. So something like this. So we have the data of this shape, and the model predicted this kind of line. It's kind of linear function. So this is underfitting because it performed very bad on training data, and also very poor generalization on the other data as well. This is good fit, is kind of preferable model. And on the right, that is the overfitting. So our model tries to hit all the samples in the training data set, and that is good, performs good at training data, but performs bad in test data in terms of cannot generalize the other data. The solution is use regularization, as Dimitris mentioned, or batch normalization, or use dropout to prevent the overfitting. Yeah, let's try some of optimization algorithms here. Okay, let's start with the importing the library and Keras layers. And we are going to train the MNIST dataset using 3 different optimization algorithms. Why is it too slow? So yeah, let's here define batch size, number of classes, epochs we want to train, and here's 2 other parameters which we are not going to use all the data set, but we are going to use a small part of data set to train faster because we don't have enough time. And this is the resolution of images, 28 by 28 in MNIST dataset. And let's load the MNIST data to memory. So basically, this is the number of samples in training dataset is 60,000 samples, and we have 10,000 samples in test samples. But let's decrease the dataset size so that we can train quickly. So I'm getting only a small part of dataset. So we have 1,000 samples for training and 500 samples for testing. So yeah, here let's define the loss function optimization algorithm and performance metrics. So regarding loss, let's keep same one, that is categorical cross entropy, but let's change some of optimization algorithms. So let's start first with stochastic gradient descent without any momentum, without any learning rate decay, and so this is another, Nesterov is another kind of method, and without any Nesterov option. So our expectation is this should perform worse than the others, right? Because here we don't have momentum, we don't have learning rate decay. Okay, let's try this one first. And here we are defining our model. So here's 2 convolution layer, 1 max pooling, 1 dropout, and 1 dense layer, and 1 more dropout and 1 more dense layer. So this is our network. So there are more than 300,000 parameters to train. And let's start training here. So this is the first epoch. The validation accuracy in the first epoch was 12, and then 19, and then let's wait for the third one, 21, 24, it's kind of converging very slowly. Yeah, and let's check the accuracy of our model on test set, which is okay. So our test accuracy was 24%. Okay, let's keep in mind this one, 24. Oh, let me write here. It was 24. And let's use SGD with, let's use directly this one, with momentum, with learning rate decay and Nesterov. Yeah. Let's compile our network with these parameters here. And let's do training again. So what we expect? So we expect the faster convergence, right? Because we use momentum, we use learning rate decay. Yeah, let's see the accuracy here. Yeah, it is 70. It was 24, right? In the previous one. So it was 70%. We didn't try this one. And let's use Adam. Again, compile the network and do the training again. So we expect even better result in when using Adam. Let's see. Yeah, it was 80. This 180. Yeah. So we did try 3 different optimization algorithms. The first one was the SGD without any momentum and without any learning rate decay. In the second, we tried again SGD with momentum and also controlling the learning rate. And there's another option is Nesterov. And the last one was Adam, which was using the second order derivative of gradients to update the weights. So it was a bit complicated, but the performance was the best among these 3 optimization methods. Yeah.